The second example is the standard enthalpy of formation, which they symbolize here as delta H standard F. So delta H naught F, F for formation. And here's how the book more or less defines this. It says if you make 1 mole of a substance, if you make it from the pure elements, so for example, water is H2O, so if I take oxygen as it exists in the pure form and hydrogen as it exists in the pure form, and I put them together and make 1 mole of water, what is the heat that's either released or absorbed for that reaction? For that reaction of taking the elements and creating my substance. That's what is defined as the delta H of formation. So I think that makes sense. You're forming something. What is the heat that's involved with that formation? Again, listing under standard conditions is typical. Alright, so what about this example? CO2. I've got carbon dioxide as a gas being formed from the elements. Carbon. Carbon comes just as single atoms in its pure elemental form. It's a solid. Oxygen comes as a diatomic gas, so it's O2 as a gas. If I put them together to get CO2, right? If I make 1 mole of that, so I balance it so that there's a 1 in front of that CO2, what is the H involved? I could look that up in a table. The H involved of formation at 298 degrees is negative 393.5. So that's actually an exothermic delta H of formation there. Alright, so often you'll see it written this way as well. Delta H formation for CO2 gas. So they just add this little comma, CO2 gas down there. And there you go, there's the actual value of it. Now this is useful because we can calculate actually, or we can predict delta H's of various reactions using the formations, the delta H of formations. In order to do that prediction, we'll need to invoke something called Hess's law. Hess's law is the idea that you can add together reactions, you can multiply reactions by a constant, you can reverse them, you can do all these various manipulations of the reactions, and whatever you do to the reactions, as long as you also do it to the delta H of those reactions, it's valid, it will properly predict what the result is. So, a couple examples for you. Let's say I have the reaction, two things, A plus B, whatever they are, reacting to give you C. And then I can turn around and take that C and react it with something else, E, to give you some final product, F. Alright, so I've got a two-step reaction. The first reaction has whatever delta H1 is. Could be positive, could be negative, endothermic, exothermic, well, whatever it is, delta H1. Then my second reaction, delta H2. If I combine those reactions together, right, so and take the C and you can turn around and react it with E right away. So if I add these two reactions together, I'm going to have a C on the left, I'm going to have a C on the right, so those cancel out. A, B, they don't cancel with any over here. F doesn't cancel. E, so just the C's cancel. So here's my overall reaction. A plus B plus E going to give you F. The delta H for this overall reaction is simply number 1 plus number 2. That's Hess's law right there. I added the reactions together. I do the same thing to the delta H's. Okay. Here's another version of Hess's law. If I take a reaction, G plus H giving me K in this case, and flip it around, can I cause K to go back to G and delta H? Sometimes you can do that under the right conditions. So if I flip the reaction, I take this inverse, if you will. What do I do with the delta H? I take its reciprocal, not its reciprocal, it's negative. So delta H here, negative delta H. So if it was a negative 100, now it's a positive 100, whatever. That's actually Hess's law, just multiplying through by a constant essentially, which is the third part of Hess's law here. M plus N going to P, if that's delta H, if I multiply everything through by a constant, I do the same thing to the delta H value. So if this was a 3 for here, then it'd be 3 times the delta H from before. Right. So let's look at 13 as an example of this. Scroll in here. There we go. Determine the delta H of formation of iron 3 chloride from the enthalpy changes of the following two processes that occur under standard state conditions. So let's take a look at this. We've got iron plus chlorine gas giving iron 2 chloride. So there's just 2 chlorines here. As that's written, negative 341.8 kilojoules is the enthalpy change. Now they're taking this and they're turning right around and reacting it with more chlorine gas to give finally the iron 3 chloride. Right? That second reaction has a delta H of negative 57.7. Right? And they say, what is the determine the enthalpy of formation of the iron 3? So they want me to go from the standard elements, iron and chlorine, all the way down to the iron 3 chloride, the product of that second reaction. Well, I think it's pretty clear. I'm going to have to add these reactions together because here I've got the iron 2 chloride and the iron 2 chloride. If I add them together, they'll cancel and I'll go directly from the elements to the iron 3 chloride. So let's try that. Here I've rewritten the reactions that we just talked about. We're saying what is it for the iron 3 chloride. We're going to add those reactions together. Right. I've done that down here. Add them together. The iron 2 chlorides have canceled. I've got the chlorine gas and a 1/2 chlorine gas. That's right here, chlorine and a 1/2 chlorine. So when I add that together, that becomes a total of 3/2 chlorine. Right? And so here's my overall one then. Iron, chlorine gas, iron 3 chloride. What did I do? I added the delta H's for them to get negative 399.5. Right? So there is, and I'm producing 1 mole of it, right? So there is the delta H of formation for iron 3 chloride, using Hess's law to do that. I can also use Hess's law for annealed reaction. That's what I alluded to at the very beginning here. You see, I can think of a normal reaction like this, NO2 plus water to give me HNO3 nitric acid plus nitrogen monoxide. I could think of that as, hey, forming these two and then allowing them to come apart, which is just the flip, the negative of them, to form these guys. What is the overall delta H for that? What would be the formation of everything I'm producing here minus the delta H of what I'm tearing apart, that is to say the reactants. And so I've got this general equation that says, hey, the delta H of any reaction is simply the summation of the delta H formations of the products minus the delta H formations of the reactants. Products minus reactants, you add them up and that predicts the delta H of the whole reaction. Looks like a scary equation, but it's actually very easy to use. Let's use value 15 as that example. So let me scroll ahead here. It says, what is the standard enthalpy change for this reaction? So we're doing it under standard conditions, so we can use the delta H's that we look up in tables for these guys right here. NO2, H2O, HNO3, and NO. All right. So I go back to my notes here. I say, hey, I can use this Hess's law to calculate this. I've got 2 nitric acids that are being produced. Right? So I'm going to start my calculation as 2 times the delta H of formation of nitric acid. Up here I'm producing 1 NO. So now I'm going to add to that the delta H formation of 1 NO. I have 3 NO2s as reactants that I'm going to be letting it come apart, so I'm actually subtracting, and 1 water, so I subtract that. So again, products minus reactants. That's simple. Products minus reactants, which is kind of, if you want to think about it, final minus initial. Okay. Of course, you have to find these values. What is delta H formation of nitric acid, aqueous, of nitrogen monoxide gas, of water, liquid, etc., etc. Your textbook has in the glossary, in the index and the appendices at the back, a table, Appendix G, thermodynamic properties, where they list substances and delta H of formation in terms of kilojoules per mole of all these various things, and it's more or less alphabetical. So here's aluminum, antimony, arsenic, etc., etc. And if I scroll down to, for example, the very first one, we have nitric acid, right? 2 times delta H formation of nitric acid. If I go up to the reaction, that's HNO3 aqueous. So if I go back and I'm trying to find the nitrogen compounds, I have to scroll to nitrogen. Oops, went too far. Okay, here we go. Nitrogen, come down here, and I do find, here's HNO3, but you have to be careful. Here's the liquid form, here's the gas form. They don't list the aqueous form. See, other ones, here's aqueous, AQ, so you have to use the right state. And this particular one, actually, the book doesn't have it. I did put a link on Moodle that shows a more complete table Here's one from the LibreText site, and they do the same thing. Aluminum, barium, all the different ones. Here's delta H formation in terms of kilojoules per mole. And so once again, I'll scroll down to the nitrogen compounds. And here we go, nitrogens. And they've got HNO3 liquid, gas. And here's the aqueous version. So negative 207.4 kilojoules per mole is what we want to use for there. Alright, so go back to here. Negative 207.4. I'm doing all of them in terms of kilojoules. Put that in. Use the same thing here. I've got delta H formation of nitrogen monoxide. Look that up. 90.2. Minus 3 for nitrogen dioxide. That was 33.2. Anyway, find all those values. Simply put them in and put it through the calculator. Turns out to be negative 138.4 kilojoules. And so as this reaction is written, NO2 gas plus water to give you HNO3 and NO, 138.4 kilojoules of energy is released. And again, that is for that reaction. So that would be negative 138.4 kilojoules per 3 moles of NO2, or per 1 mole of H2O, etc., etc.